This video will cover section 5.1. Now, section 5.1 deals with what we in calculus call the area problem. And the area problem, it's quite simple. Here's what we know about area right now. Most of us know how to find the area of a polygon, like a rectangle, right? We can find the area of a rectangle. We have a formula from elementary school that tells us the area of a rectangle. We can even find the area of a right triangle because we know half base times height. If they give us one of the mean triangles that doesn't have a side that's vertical, we have trigonometry that helps us find the height of the altitude, and we can use half base times height there again. And then when it comes down to not almost, but any polygon, right? Any polygon we draw, we could, if we wanted to, draw and cause that polygon to be broken into triangles, and we could find the area of this triangle, the area of this triangle, and the area of this triangle. And we could use triangles to find the area of any polygon. Where things get a little trickier is when we want to find the area of a shape whose sides are curved. Now, if we're starting with the circle, we don't have anything to worry about, right? If we have a circle, I'll just grab this protractor. If we have a circle, we have a very definite formula for the area of the circle, and we know exactly how to find the area of the circle. And if any part of our curve is the edge of a circle, then we're safe. We can find the area of that. We know the area of a circle is pi r squared. But what happens if it's not a circle? What happens if the curve that we have to deal with doesn't look like the arc of a circle? If it's not the arc of a circle, what are we going to do then to find its area? And, let's make this look like a calculus problem. We'll just draw ourselves a function here. We have a function that goes like this. And we'll pick this edge, and we're going to call this A. And we're going to call this edge over here B. And we're going to want to find the area of this region right here. How would one go about finding the area of that? So if f is continuous, on the closed interval from A to B, how are we going to find the area of that region? And to make this simpler, let's just go ahead and assume that f of x is greater than or equal to 0. We'll put the region above the x-axis. We're going to talk about what happens if the region falls below the x-axis, and we have a pretty simple solution for that, to be perfectly frank with you. But for now, we're just going to put the region above the x-axis. So what are we going to do? How are we going to find the area of this? And the answer is we're going to use limits. Ultimately, that's where we're going to go. We're going to get this all the way to limits. It's a calculus problem. All calculus problems seem to eventually find their way back to limits, and this one is going to do exactly the same thing. But how are we going to start, right? What are we going to do in the beginning? And how can limits have anything to do with this picture? That's our journey in section 5.1. So let's take a look at this picture and let's just ask ourselves some questions about this, right? For example, if I just chose an endpoint, and in this case I'll pick A, and I made a rectangle, we all know the area of that rectangle is not the same as the area that we shaded in under the curve. We can see that. We can look at that and we can say, yeah, that's clearly not the same. And the reason it's not the same is because we have this entire region right here included in our rectangle, but that region is not included, right, in our shaded area. So we would be overestimating. In this case, we would be overestimating our true desired result, that being the area that we shaded in. Now, what happens if I draw a horizontal line from the other end, right? I come across this way. Now, why am I drawing these horizontal lines? Well, I'm drawing horizontal lines because they make rectangles, and I can find the area of a rectangle, right? I know how far it is from A to B. It's B minus A. And I can determine this height. This height is f of b, right? That's how tall this is right here. This is f of b tall. And I know how tall it is over here. This is f of a tall. So for our red rectangle, right? For our red rectangle, the area is going to be the height, f of a, times the width, b minus a. And for our purple rectangle, right, for our purple rectangle, the area is going to be f of b, right, the height, times the width, which again is b minus a. Now, we know something about both of these results, right? We know they're wrong. That's what we know. And the reason they're wrong is because the purple rectangle leaves out this piece, whereas the red rectangle includes this piece. So we know this one, right? This one, too large. And this one down here is too small. All right? So we have those, and what are we going to do about this? How are we going to fix this, right? This would be great if we could use something as simple as this to find the area of that region. That would be a great approach, right? That would be, I would say, an approach that most of us could handle, because after all, it involves finding the area of rectangles, and the area of rectangles, we're pretty good at those, right? That's something we can do. Now, perhaps some of you had the thought, well, we'll just take the average of these. Well, I'm going to agree with you that if you take the average of those two, you're going to get a closer answer, right? You're going to get an answer that's more accurate, because this one is definitely way too small and the red one is definitely way too big. But that's not going to give us the right answer, is it? It's just going to give us an approximation. And for that matter, we could have used the purple rectangle as an approximation, or we could have used the red rectangle as an approximation. So what we need is an approach that's going to help us, right? That's going to help us overcome the fact that this endpoint ended up too small and this endpoint ended up too big. And of course, I could draw another function, and then those roles might be reversed, right? This side may give me something too small. This side may give me something too big. It just happens that my function is decreasing from A to B. And so these roles would be reversed in terms of who's too big and who's too small if our function was increasing from A to B. Well, let's just ponder this for a second. We used the endpoints and we made rectangles. And we ended up with arrows, didn't we? But what would have happened if we would have just split the region in half and made, instead of one rectangle, two rectangles, right? So what have I done? I've given myself another place to determine height. That's what I've done. I've chosen this spot right here. We can call this spot anything we want. We'll just call it X, okay? Now, if I go from this endpoint here, and I come across, and I go down, and then I come from this endpoint here, and I go across, and I go down, and I use two rectangles, right? What about two rectangles? That's the question. Right? What about two? What about two? Well, if we take a look at our picture, right? If we take a look at our picture, we can see an improvement. There's an improvement here over what we had done before. What we did before with the red, right, with the red, we have eliminated part of our error. This right here, right, this part of our error is no longer included. With our two rectangle approach, we have literally eliminated that part of our error. That part's gone. Now, we were too big before. That's what we said. We said the red rectangle was too big, and it was. We could all see it was too big. But now, because we have two rectangles, we'll draw them again. Because we have two rectangles, we're still too big. We can all see we're too big. We have this piece right here, which we don't want. We have a lot of white down here that we didn't want. We wanted the blue region. So by using two rectangles, we got a better, not a good, but a better approximation for the area of the region that we were asked about. So then the question becomes, if two rectangles got us a better answer than one rectangle, will more than two rectangles get us a better answer than two rectangles? What would happen, right? What would happen if instead of two rectangles, we once again, right, we once again split this. And instead of two rectangles, we split it into four rectangles. All right, we split it into four. Now I have 1, 2, 3, 4. So the question that follows, what about two rectangles, is what about four rectangles? Is this going to be better than what I saw with two rectangles? And the answer is yes. If we redraw this, right, and there's a lot of lines up here, I understand that, and there's a lot of colors, and you're going to have to, maybe you have to pause the video and take a look and make sure you can see all the colors and what we're trying to convey here with this picture. But if we now do this with orange, right, orange is going to come across here to this end point. Now, where do we go from here? Well, we still move across here like this. Okay. We're still counting this. This is still one of our height determining points on the x-axis. So we have one rectangle, two rectangles, three rectangles. So this one's going to come across here, but now it's going to stop. It's going to stop right here, isn't it? And now this rectangle is going to go from this height, and it's going to come across this way. And if we look at this closely, right? If we look at this closely, have we improved our situation? And the answer is yes. Yes, we have. We've improved our situation because now the orange rectangle comes across down here. From this point, the height is determined here, right? It's the height of the function that we're using as the height of our rectangle, the height of the function times the width of the rectangle. It's just now we have 4 widths, whereas before we had 1. And now we've eliminated this. This error is gone, isn't it? And so while we're still too big, right, we're still too big, we have this piece now we didn't want. We have this piece now we didn't want. Our error is substantially smaller than it was. Remember, one rectangle looked like this. So all of this error here, which is a substantial amount, all of that error has been eliminated by us moving from one rectangle to 4 rectangles. And now perhaps you've begun to think this through, because remember, when we started the video, we said this is going to end up talking about limits. It's a calculus topic. Calculus topics weeks end up talking about limits. So this is going to end up talking about limits. And so perhaps you've been able to move ahead of where my development is and gotten to the point that you understand how limits are going to play a role in this. If not, that's okay, because I'm going to talk to you about that right now. How are limits going to play a role in this? Well, limits are going to play a pretty simple role in this. And that the role here's how limits come into play. Right? One rectangle was too big. Two rectangles was better, still too big. And we're talking about rectangles that start from the left, right? When I say too big. If we were going to do this from the right, I would be saying too small. So let's just stick with one direction. And let's say we drew our rectangles this way. One rectangle was too big. Two rectangles was still too big, but it was better. That's the important part. It was better. Four rectangles was still too big, but it was much improved over one rectangle. I think hopefully by now you've determined where this is going to go. If one rectangle was too big and two rectangles was still too big but better and four rectangles was still too big but better, then we can probably see that 8 rectangles is going to be better than, I'm not going to draw it, but 8 rectangles is going to be better than 4 rectangles. 16 rectangles is going to be better than 8 rectangles. 32 rectangles is going to be better than 16 rectangles. And on and on and on until we, you and I, come to the conclusion that an infinite number of rectangles is going to be the best answer. That's where we're going in section 5.1. That's the journey we're going to take during this development. We're going to start here with the idea that one rectangle gave me an approximation, but it was too big. 2 rectangles gave me an approximation, also too big, but better than 1 rectangle. 4 rectangles, also too big, but better than 1 rectangle and better than 2 rectangles. And then if we continue this game on, right, over and over and over, we can get as many rectangles as we want to draw. And with the beauty of calculus behind us and the power of calculus to assist us, we can draw an infinite number of rectangles. And if we draw an infinite number of rectangles, we're going to get the true area under that curve. Now, you and I both know that we're not going to be able to draw an infinite number of rectangles. So that's going to be our journey. Our journey is going to be, how do I do what Kevin has said I should do, which is draw an infinite number of rectangles. How is that going to be possible? What steps am I going to have to follow to make this a systematic and doable process, right? That's what we're going to talk about today. So let me clean this off. And let's get into the nuts and bolts of this journey that we're going to take today and see if we can come up with a solution for the area problem. Okay? So we're going to use a very classic example. This example is in almost every calculus book, to be honest with you. So if you're not using the same book we're using in our course, which is, Stewart's 4th edition, this example is more than likely going to be in your book as well. So we're going to consider f of x equals x squared, all right, our friend the parabola, from x equals 0 to x equals 1, okay? That's how we're going to begin this process. So over here on the side, I'm going to draw just a sketch, right? Just a sketch. And we have our parabola, and it goes like this. Okay? This is the point 1, 1. And this is f of x equals x squared. Right? And we're tasked with finding the area enclosed by this region. Okay, that's our goal. That's our task. Now, you and I have already determined that one rectangle is probably not the best approach. If we were to just, I'll use a ruler here, if we were to just do one rectangle, let's just start with the obvious, right? This is our left-hand endpoint of our region right here. If we were going to use that to determine the height of our rectangle, right? We know what the width is. This is 1. This is 0. So the width of our rectangle is 1. But the height across here, right? The height across here, if we use that side as our height, remember what we wrote earlier. We said we're going to use f of a as the height, and we're going to use b minus a as the width, and that's how we're going to get our area. That was one of our approaches when we had one rectangle. We said we're going to take the left-hand endpoint. That's going to help me with my height. I'm going to have my width. Well, our height right here is 0, right? This would be 0. And our width would be 1. And we would get 0 as our estimate. If we used one rectangle, it would come across here, just like this. And our rectangle would have no height. And we would have an answer of 0. Now, the other option we chose with one rectangle, right? The other option we chose with one rectangle was not to start with f of a. We didn't choose that. We said, well, we could start with the left-hand side. The other option was we could start with the right-hand side. And if we did that, that would be here, right? This is our right-hand side. We're looking at our interval, and we're saying this side is on the left and this side is on the right. So when you hear me refer to right-hand side, I'm talking about the side on the right. So what does this look like, right? What does it look like? Well, if we draw this rectangle, right? We'll just draw this rectangle up here. We would get this rectangle because our height would be over here. Our height would be f of b. b is 1, right? F of 1 is 1. So that would give us 1. Right? This is going to be our area. Our width would be 1, and we would be telling the reader, telling the person who asked us for the area of this, we'd be telling them that it's 1. And we know that's wrong. There is a large error. All of this up here is an error. We have overestimated by a lot, right? So we know that if we used one rectangle, that would not give us the correct answer. So this fits the approach that you and I were talking about just a second ago with our general drawing, right? This is a specific example, but with our general drawing, we said, well, one rectangle doesn't come very close. Perhaps we should use more than one rectangle. So what we're going to do here is we're going to use 4 rectangles. Okay, we're going to use 4 rectangles. Because we've already, with our previous little sketch, we've already decided one rectangle is probably not good. 2 rectangles is better than 1, but not accurate. 4 rectangles was better than 2. Now we know when we do this over here, we're not going to get the correct answer. But we're going to use 4 rectangles as our jumping off point. Okay? And then we'll increase the number of rectangles maybe in our next example. So we need to talk about some notation here. All right? If we're going to make 4 rectangles, what do they expect us to do? Well, they expect us to, the word we're going to use is subdivide. Right? We're going to divide this into what we call subintervals. 4 subintervals. Our interval is from 0 to 1. These are subintervals. And if we draw this, our assumption is going to be if I say 4 rectangles or 8 rectangles or 12 rectangles, that we're going to make our rectangles have equal width. So in the problems we're going to work in the homework, we're going to assume the width is equal. So when you see me make these hash marks, what have I done? Well, I bisected this. We all know where that lives. That lives at a half. Then I bisected this piece, and that's going to be 3/4. And then I bisected this piece, and that's going to be 1/4. Okay. So, where do we go from here? Well, now we need some notation. When someone tells me I want to use 4 rectangles, what they also have to tell us is, am I using right-hand endpoints or left-hand endpoints? So let's have a conversation about that. What does right-hand endpoints mean? Well, it's quite literally just exactly what the words say, right? Right now, you and I, we have subdivided this into 4 sub-intervals. We have this one, we have this one, and we have this one. So our intervals go from 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, 3/4 to 1. Those are our sub-intervals. And then the question becomes, how am I going to determine the height? What am I going to use? Am I going to use right-hand endpoints? Or am I going to use what we're going to refer to as left-hand endpoints? Right-hand endpoints are exactly what the term says. A right-hand endpoint means we're going to take this subinterval right here, and we're going to choose the right-hand side. The right-hand side being 1/4, and we are going to use 1/4 to determine the height of our rectangle. Okay. Then we're going to come to this interval, and we're going to take the right-hand side. The right-hand side is going to be 1/2. And we're going to use 1/2 to determine the height of our rectangle. Hang on just a second. I just want to check something here. I'll be right with you. Sorry about that. I had to pause the video there for just a second. All right, so on we go, continuing to use the right-hand side, right? The right-hand side as the side that determines the height of our rectangles. And this is what our picture would look like if we use right-hand endpoints. I use this side to determine my height. That side is on the right of this interval. I use this side to determine my height. That side is on the right. I use this side to determine my height. That's why my rectangle is that high, right? It comes from here, f of 3/4. And then here I used f of 1 to determine my height. This problem, if they gave us this problem in the book and it said, use this function from 0 to 1, use 4 rectangles, use right-hand endpoints, approximate the area. That's how this problem would read. So how would they write that? Well, what's some notation we have to bring into play here? When someone says right-hand endpoints with 4 rectangles, you're going to see them write this, R sub 4. R sub 4. R meaning right hand, 4 meaning four rectangles. Okay, or 4 sub-intervals. Now, is there another way that they could present us this problem? Yes, there is. They could present us the problem. It could say, use 4 rectangles. And it could say, use left-hand endpoints. Okay, left-hand endpoints. Now, their notation for that, or our notation for that, would be L sub 4, meaning 4 subintervals using left-hand endpoints. Now, what would that picture look like? I'll use red to draw that. We come back to this subinterval here. This is our first subinterval from 0 to 1/4. We would use the left-hand side to determine our height. Now, our left-hand height is 0. When we plug 0 into our function, we get 0. So our first rectangle would be this one right here. It would have a height of 0. Our second rectangle, right, we would have this as our second subinterval. So our second rectangle would use 1/4 as my left-hand side, and I would have a rectangle that looks like this. And then my third subinterval, I would have 1/2 as my left-hand side. 1/2 is the left-hand side of this. And I would have a subinterval that looks like this. And then finally, my last subinterval, I would have 3/4 as my left-hand side. And 3/4 would give me a height. 3/4 is right here, so that would give me a height of this. Now, if we look at this, now it's going to take a second for your eyes to get accustomed to what I'm going to say. So I'm going to use my pins as pointers here. The right-hand approach are the green rectangles. Now, make sure you see the whole rectangle. This rectangle goes from a height here all the way down to here. This rectangle goes from here all the way down. This rectangle goes from here all the way down, and this rectangle goes from here all the way down. Now, what would they ask us to do in a homework problem, right? They would say, find R sub 4. Now, that is going to become just a glorified arithmetic problem for us, right? If we had to find R sub 4, what would we say? We would say, well, I have a rectangle right here. I have this green rectangle. I'm using green because we're using the green rectangles. How wide is my rectangle? Well, my rectangle is 1/4 wide. How tall is my rectangle, right? Well, my rectangle is f of 1/4, right? The function tells me how tall it is. What about my next rectangle? How wide is this rectangle? Well, my rectangle is 1/4 wide again. How tall is my rectangle? We're doing right-hand sides. Right-hand side is this one. So my height is f of 1/2. We keep going. This side, this subinterval is 1/4 wide. So we get 1/4. And our height there is going to be f of 3/4. And then finally over here, we get 1/4 wide times our height, which is f of 1. So when we do these problems in section 5.1, and they ask us to find R sub 4 or L sub 4 or R sub 6 or whatever they ask us for, they turn into these glorified arithmetic problems. Now we know this answer is wrong. They didn't ask us to find the real area. They asked us to approximate the area with 4 subintervals using right-hand endpoints. And that's what we've done. Now, we haven't done that yet. We have to finish. Now, what does this... Well, if we take a look at this, there's a 1/4 in every one of these, isn't there? So we're going to factor out a 1/4. We're going to factor that out. Now, what's f of 1/4? Well, my function is x squared. 1/4 squared is 1/16, isn't it? Now, I'm going to give you a bit of a hint here. Early in the game instead of later in the game. I'm going to give it to you now before you do the homework. A lot of times we save this hint until you come back with questions. When you square 1/2, we all get 1/4. We all do. Everybody gets 1/4. 1/2 squared is 1/4. That makes complete sense. But if I write 1/4 here, I don't have a common denominator. And I'm going to want to add all these numbers up. When I square 3/4, right? When I square 3/4, I'm going to get 9/16. And when I square 1, I'm going to get 1. Now, there's a better way to do this. Right? And you know what it is. If you think about it, you know what it is. The better way is not to write this as 1/2. The better way is to come back over here and to write this as 2/4. And instead of writing this as 1, we're going to write this as 4/4. Because why? Why would we want to do that? Well, because patterns are going to become the key to getting these problems correct. And if we can keep all of the denominators the same, right? If we can keep all the denominators the same, then what happens when we square 2/4? When we square 2/4, instead of 1/4, we get 4/16. And when we square 4/4, instead of 1, we get 16/16. And now we are already set up with common denominators, aren't we? So now when we add these together, it's going to go much quicker, much simpler, much easier. So what do we have? We have 1/4, right? We have 1/4 times, and we have 9 plus 1 is 10, 4 plus 16 is 20, and we have 30 divided by 16, don't we? And now can we simplify that? I think we can, right? We can divide 2 into here and 2 into here. That gives us 15, and that gives us a 2. And we end up with 15 over 32 as our right-hand estimate with 4 subintervals. Now, you and I are both fully confident that that is wrong. We understand that is wrong. We have all of this area we did not want. And when I say all of this area we did not want, I mean this piece right here. We did not want that, but we included it in our answer because we've only allowed ourselves 4 subintervals. And likewise, we have an error here, and an error here, and an error here. This is an overestimate, right? It's too big. It's an overestimate. Now, how else might they present this problem? They might ask us to find L sub 4, right? Find L sub 4. And we've already drawn L sub 4 over here. We know L sub 4 is going to be too small. L sub 4 is just going to be these rectangles right here. This one's going to go to here. This one's going to go to here. This one's going to go down here. And that one actually has a height that's 0, which means we left out, right? We left out all of this, and all of this, and all of this, and this entire piece right here. We left all those out. Those are not going to be included here in L sub 4. So L sub 4 is going to be an underestimate. We can see that before we start because we made a sketch. But we're just approximating. We're building our understanding so that we can eventually get this from 4 rectangles to, remember, our ultimate goal. Our ultimate goal is an infinite number of rectangles. And we're a lot closer to that than you think. So what would L sub 4 look like? Well, again, we're back to our analysis. I like to personally put my fingers down and say, well, this is the left-hand endpoint. So how wide is that interval going to be? It's going to be 1/4 wide, and we're going to find f of 0, right? That's my left-hand side. How wide is this interval going to be? 1/4 wide. Who's on the left-hand side here? The left-hand side is 1/4, right? 1/4 is the left-hand side, so that's going to be f of 1/4. That's how tall this red rectangle is. F of 1/4 is right there, and that gave me my height. I come here, I'm using left-hand sides. This is the left-hand side. We're going to use our 2/4 this time to shorten our workload. So our width is still 1/4. It's still width times height, just like in elementary school. So this is going to be f of 2/4. And here, 3/4 is on the left. 3/4 is on the left. Our width is still 1/4. So we're going to have 1/4, and we're going to have f of 3/4. Just like up above, everybody has a factor of 1/4, so we can factor that out, right? F of 0. 0 squared is 0. So that's 0 over 4, right? 0 over 4, because I want to get my common denominator. I square 1/4, I get 1 over 16. I square 2/4, I get 4 over 16. I square 3/4, I get 9 over 16, right? 9 over 16. And so what do we end up with? We end up with 9 plus 1 is 10 plus 4. So that is 1/4 times 14 over 16, right? And once again, we can divide here, get this to be a 7, this to be a 2, and we end up with 7 over 32. 7 over 32 is smaller than 15 over 32, right? And this is an underestimate. So in our homework problems, for most of the questions they're going to ask us to complete, this is how we are going to approach our solutions. Our solutions are going to be based on us drawing subintervals of equal width and drawing the appropriate number of rectangles. Whatever this subscript is, it might be 4, it might be 6, it might be 8. Then we are going to draw an appropriate number of rectangles. Based on that, we'll partition, is the word we're going to use. We'll partition our interval into this many sub-intervals. And that will allow us to come up with a picture. And then we have to remember, if it's right-hand side, we pick the right-hand side. If it's left-hand side, we pick the left-hand side. And then we use that to determine our height. And so you can go back and watch this video, take a look at this drawing, right? Take a look at this drawing, and then make sure that we are acclimated, right? Acclimated to what's going to be the left-hand side and what's going to be the right-hand side. Now, at the beginning of this, I promised you that the journey, the ultimate journey here, was going to be to take this from 1 rectangle to 2 to 4 to an infinite number of rectangles. And so we're going to take our picture here, and we're going to take that journey. We're going to take that journey and ask ourselves, what is this going to look like with an infinite number of rectangles? So let me erase this. Let me erase this, and then we're going to redraw it, and we're going to ask ourselves, what is it going to look like, right? What's this going to look like with an infinite number of rectangles? So what we're going to do here is a bit of foreshadowing. It's closer to what we're going to be asked to do, to be honest with you, in section 5.2. But we're going to talk about it here in section 5.1 because Stuart talks about it in section 5.1. He introduces this approach in section 5.1. So what does he say in section 5.1? He says, well, what about, right? An infinite number of rectangles. What is that going to look like? So let's come back over here. Let's draw our function again real quick over here. And if we draw f of x equals x squared again, right? We have this. So from here, the last time we approached this, we said, well, we're going from 0 to 1. And I want 4 rectangles, right? I want 4 rectangles. Well, now the question is grown a bit. So how do we write this, right? What's our notation for this going to look like? Well, believe it or not, it's going to look like this. We want to take the limit as n approaches infinity, and I'm going to use right-hand endpoints, r sub n. Right? This is the actual area. Okay, that's the actual area under this curve from 0 to 1. That's going to give us the actual area. Because why? Well, every time we increase the number of rectangles, our error got smaller and smaller and smaller. We showed that in our very first picture where we had the function going across the top of the screen. I kept erasing little pieces and saying, well, look at that, our answer's better. Oh, look at that, our answer's better. As the number of rectangles grows, the error gets smaller. So if we let the number of rectangles grow without bound, the error, therefore, logically is going to go to 0. So that's the journey we want to take with this problem. Now, how are we going to do that, right? What are we going to do? How are we going to do an infinite number of rectangles? Well, let's take a look at our picture over here. And now we're going to focus on this in the beginning, r sub n. Okay? We'll worry about the limit at the end. So I'm going to write that over here. We're going to save the limit. It's the best part anyway, right? Save the limit until the end. We don't want to be worrying about the limit right now. We're going to worry about r sub n. So we're going to consider r sub n. And this is just it's a logic exercise. We're going to ask ourselves, all right, if I'm going to consider r sub n, I need n intervals over here. N of them, right? I need n. My subintervals are going to be smaller. Now, I can't draw n intervals here, but I'll draw a few. And we're going to ask ourselves, how many intervals do I have, right? I have n of them. I have n. So how wide is each subinterval? How wide is each subinterval? Well, that question was easily answered when we had 4 subintervals. We took the length, right? That's what we did. We took the length and we divided it by the number of intervals. And we came up with 1/4. We didn't even really talk about it. It just happened, right? Logic told us, well, I go from 0 to 1. I need 4 of these. They're each going to be 1/4, and we were on our way. Now we're going to have to think about it a little longer. We have our length, which our length is 1. And how many subintervals do we have? We have n. Well, that's the width of each interval. Now, we have a fancier way of writing that, and we'll get to the well, let's just put it down right now. They kind of save this till later in the development. It comes up in section 5.2, to be honest with you. But we might as well talk about it right here. We called this person A back in our very first example. We're going to stick to that. That's standard. We call the right-hand person B. And so we can take this length divided by number of subintervals. And we can, hey, we got some room right here. Well, we'll just use it. We can say, well, our length is always going to be our right-hand endpoint minus our left-hand endpoint. Right? 1 minus 0, this is 1 long. If this was 7, right, just play along with me here. If that was 7, and this, I understand it doesn't look right, but if this was 3, everybody in the room knows, and everybody everywhere knows that this is 4 units long. 7 minus 3 is how we got there. So that's all we're saying here. Take the left-hand side minus right-hand side. That'll tell you how, let's get these off here. They look kind of silly. That tells you how long. And then the number of intervals we have in this case is n. So b minus a over n. 1 minus 0 divided by n is the width of each interval. Now what does that mean? Well, that means we can write them down. We know we started at 0, we moved 1 over n. Well, that means we landed on 1 over n, didn't we? And then we started at 0 and we moved our second interval, which is also 1 over n, isn't it? So how wide was our first interval? 1 over n. How wide is our second interval? 1 over n. So where is the end point here going to be? It's going to be 2 over n because this is 1 over n wide. And this is going to be 3 over n, and this is going to be 4 over n. And on and on and on this is going to go. Now, what are we going to get at the end? Well, do you remember that little trick I showed you previously about, hey, we should stick to common denominators? I think if we want to call this, which we do, 1 over n, 2 over n, 3 over n, 4 over n, then we want to call this one down here, yep, you're right, n divided by n. And in fact, to stick with our program, we should call this very first one 0 divided by n. And that's going to make our pattern more prevalent as we start to solve this problem. So what does R sub n look like? Now remember, when we did R sub 4, it turned into a glorified arithmetic problem. That's what it did. And so is this. This is also going to turn into a glorified arithmetic pattern. If we want to write down R sub n, right-hand endpoints, n subintervals, what is that going to look like? Well, it's going to look like a bunch of rectangles, just like it previously did. However, we can't draw all the rectangles this time, all right? That's not possible. It's not possible for us to draw each rectangle because we have n of them and we don't know what n is. So when we draw our rectangles right now, I'm going to draw the first 4 rectangles, right? And then over here, I'm going to draw the last rectangle. Now, there are a lot of rectangles between our 4 sub n, and of course this is n minus 1 over n. It's the interval that comes 1 before the nth interval. So that is our picture. And we don't know, right? There's an indeterminate number of rectangles that go in between here. But that's going to be okay, because we're going to be saved when we do this arithmetic by the pattern. Now we're going to write the pattern down just like we did on the previous example with 4 rectangles. We're going to say, okay, well, this is my first rectangle. Its width is 1 over n, right? Now remember, our function here, right? I didn't write it down. I apologize for that. Our function is f of x equals x squared. Now what's my height going to be? It's going to be f of 1 over n. Why 1 over n? Why this side? Why am I putting this side down? Yes, you're right, because it said right-hand endpoints. So I'm picking the right-hand side. Now I switch to this. This is the right-hand side. How wide is this interval? 1 over n. So this is going to be 1 over n, f of 2 over n. Next, we're going to have this interval. This one's on the right-hand side. It's 1 over n wide. Next, we have this one. This is on the right-hand side. It's 1 over n wide. And this is going to keep going until we get to our last rectangle. Our last rectangle has this on the right-hand side. It's still 1 over n wide, though, so we still get 1 over n, f of n over n. And now, believe it or not, that math is not that hard. All of you can do that math. We're going to do exactly what we did with 4 rectangles. We're going to factor out the 1 over n. We're going to go ahead and expand these. Now, our function is x squared. 1 over n squared is, if we want to be honest, right, well, we can just write it if you want. It's 1 over n squared. This is going to be 2 over n squared. This is going to be 3 over n squared. This is going to be 4 over n squared. And this pattern is going to keep going until we get to here, where we're going to have n over n squared. Now that actually simplifies to something that you and I, know how to take the limit of. If we just clean this up, right? If we clean this up, here's a 1 over n, right? That was our width. We factored it out of every term. But look at every one of these. This is 1 squared over n squared. That's 2 squared over n squared. That's 3 squared over n squared. That's 4 squared over n squared. That's n squared over n squared. This actually looks like this. It looks like this. Now, believe it or not, we know what that is. We know what that is. We, back in pre-calculus, were given a formula for this. We probably forgot. It's not a big deal. Nobody expects you to remember it. In fact, we remind you of the formula in section 5.2. Here, we just write it down and act like, oh my goodness, I can't believe you didn't remember that. So what does this look like? This looks like 1 over n cubed, right? 1 over n cubed times 1 squared plus 2 squared plus 3 squared plus 4 squared plus ... plus n squared. Right? Now, where did I get the n cubed? I factored the n squared out here. Now, again, we forgot the formula for this. I understand that. But the formula for this, right? The formula they gave us back in pre-calculus, and we'll write it over here. The formula they gave us for 1 squared plus 2 squared plus 3 squared plus all the way out to n squared. They gave us a formula in pre-calc for that. They said it was n times n plus 1 times 2n plus 1 all over 6. And if you remembered that, great job. If you didn't remember that, don't worry about it. We're going to cover that formula in section 5.2, and we now have to remember that formula. As you can see, it's going to become part of doing our problems. Now, if we use that formula, what does this look like? It looks like 1 over n cubed times, and all of this simplifies to n times n plus 1 times 2n plus 1 all over 6. All right? That's what it looks like. Now, if we now go all the way back up here to blue, all the way back up here. Remember, we were supposed to find r sub n. We did. We found it right here. And then we were supposed to take the limit of that. So we'll go back to blue here. Now we're going to do the limit. We did all of this purple work in this drawing simply to get to here. Now the actual area, right, we said the actual area is going to be the limit as n approaches infinity of r sub n. Now for us, that's the limit as n approaches infinity of this. This is going to be n times n plus 1 times 2n plus 1 all over 6n cubed. And that's a limit that we know how to evaluate. We don't need L'Hopital's rule or anything fancy to do this limit. We know how to do this limit. The degree of the numerator is 3, n times 2n, right? This is going to look like this. It's going to look like the limit as n approaches infinity. Our leading term in our numerator is going to be 2n cubed. Plus, and there's a lot of other things that are going to come, right? Down here we have 6n cubed. And we know that if the degree of the numerator, right, if this is a rational function, if the degree of the numerator equals the degree of the denominator, as the limit goes to infinity, the answer is the ratio of the leading coefficients. That is how you evaluate this limit. We divide by the highest power of n in the denominator, n cubed. We divide everybody by n cubed. We end up with 2 over 6, and that gives us our actual area. Our actual area of this is 1/3. 1/3 is the actual area. So this is how we are going to find the area. We're going to find the area using this process right here. Now, I'm going to write down a formula for this, a formal formula for this, and then we're going to be done with section 5.1. The formula that I'm going to write is literally this line right here, right? This line here. We're going to write a general formula for this line. And that is going to be our concluding moment for this section. We'll say, okay, well, so this is the formula. But this is the process. This is what we do. If we do this, if we draw our subintervals over here, if we label them accurately, if we keep track of who's on the right, who's on the left, then we can come up with a pattern. This line will always produce a pattern. And as long as we stick with common denominators, the pattern should pop right out at us, and we should end up with something that we can reduce to a limit that we can evaluate. Okay? So, let me erase this. We'll write down the general formula, and that'll be the conclusion of this video. Okay? So what have we come to as our conclusion, right? What have we come to? We've said this. Here's what we've said. The area of a region S, right? We're going to call it S, that lies under the graph. And remember, we'll talk what happens if the graph is below the x-axis later. Right now we're going to assume all of our graphs are above the x-axis. Lies under the graph of the continuous function f is, what is this area? It is the limit, right? That's what we just discovered. It's the limit of the sum of the areas of our, now we're going to call those our approximating rectangles, because we know they're not, right? They're not really the actual area. We're going to say those are our approximating rectangles. Now, it doesn't matter whether we use right-hand endpoints or left-hand endpoints here. I did the example with right-hand endpoints. It would have worked out to be 1/3 if we used left-hand endpoints. Now, how are we going to write this, right? How are we going to write this? We're going to say, well, the area is, and we're just going to write the formula you and I wrote previously, but it's going to look, a little more general now. Oops, there's an I in there, isn't there? It's the limit as n goes to infinity of r sub n, right? So we're writing it in terms of this, and we're going to say, what does this look like, right? What does this look like? Well, it looks like the limit as n goes to infinity, right? N goes to infinity of our width, right? Our width. And we said our width was, well, we're going to call our width, which you and I called b minus a over n, didn't we? We're going to call that the change in x. I told you this was going to look a little more general than what we just did, but it's not, don't get lost in all this notation. If you can do the layman's find the area of each rectangle, you're going to be fine in section 5.1. This is kind of foreshadowing to what we're going to get to in the next section. So we're going to call this width the change in x. We're going to call that delta x, right? Delta x for the change in x. And then our height, right? Our height, we called that f of, and then when we made our interval over here, right? Our interval started here at a and started here at b, and we had our sub-intervals going like this. We're gonna label these x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub n. We're just gonna, because generally we're not gonna know who these numbers actually are, so we're just gonna use subscripts on the x-axis to enumerate them. So what's our height going to be right here? Well, our height is going to be, if our function is going like this, our height, because we're using right-hand endpoints, our height is going to be f of, well, that's two f's. Nobody wants two f's. Nobody wants one f. So our height is going to be whatever x we happen to use. Here it's going to be x of 1, here it's going to be x of 2, here it's going to be x of 3. So this definition looks like this, right? It says, well, you're going to take your width. We're going to call that delta x. We're going to multiply that by your height, f of x1. We're going to multiply that by your height. And then we're going to take your width, which is delta x, and we're going to multiply that by your height, f of x2, right? Because that's going to be our height right here. Our height here is going to be x of 2. And then we're going to take our width, delta x, we're going to multiply that by our height, f of x sub 3, and then we're going to keep going, and we're going to close out with our width times our height, f of x sub n. Right? So that's our general definition, and again, I'm not that concerned with your love or hate of this general definition right now. We're going to see this definition in section 5.2. We'll explain it more in depth in section 5.2. So this, like I said, is a bit of a foreshadowing of what's going to come our way in section 5.2. All right, that'll conclude, our video on the area problem, which in our book is section 5.1.